also thanks for hosting this great series. I was actually looking through the talks, and there's a lot of really interesting both past and upcoming talks. So I think this is a great series for the community. All right, so the brief outline here of what I'm going to be covering today, I'm going to give some background and go over really what motivates me to work on analog in-memory computing. And I'm definitely more on the device and circuits level, but I've gotten into this architecture a little bit of analog in-memory computing because I think it's going to be important for the future. And so that's kind of what I'll cover there. And then I'm going to cover the three sort of devices that I've spent a lot of time on, which actually I think represent a huge range of the analog in-memory compute candidates and neuromorphic computing device candidates that exist now. And then end up with a perspective kind of based on my work in IRDS, where we really sit around and look at all the devices and kind of try to rate and compare all of the devices. All right, so let's get started. So the first thing I like to show, and I've been showing similar slides for about 10 years, but kind of updating them. And this has actually become increasingly important over that time. I've always been very passionate about this, but I've noticed recently this is becoming widely understood that energy efficiency is really the most important challenge in computing nowadays. And the interesting thing is, computing has always been really all about energy efficiency. Now, in architectural terms, typically in terms of operations per second per watt, the physicists working on kind of emerging paradigms like to put this in terms of energy per computation. But either way you look at it, there's a very interesting trend, and I think not everyone's aware of. Since the beginning of computing in the 1940s, the energy efficiency of computing systems has been improving exponentially, basically decade over decade, by about 1 to 2 orders of magnitude every decade. And this is starting in the 40s, so before Moore's law, and it's gone kind of after Moore's law. So it's not just due to transistor scaling, but it's due to things like putting vacuum tubes together on chips, or even just going from vacuum tubes to transistors. Actually, that was some of the early work, going from vacuum tubes to transistors, then putting multiple transistors on a single chip. And then we got to the area of Dennard scaling, which was reducing the transistor current voltage. Of course, that reduced power, and so that improved the energy efficiency. And Dennard scaling continued until about 2005. So around the time I was in grad school, that was ending. And what kind of was realized around then is that, well, so transistors are not going to give us the free energy efficiency improvements. Most of the energy efficiency improvements were coming from transistors from the 70s to about 2005. So that's what really started in 2005, this big architectural push. And Intel tried to move toward parallel processor. I mean, they did move toward parallel processors, but really that was a big important era for companies like NVIDIA that already had a huge amount of expertise in parallel processing. And so then we saw things like the GPU and general purpose processing GPU really take off, and then these newer architectures like TPU, and they were really squeezing all of the energy efficiency possible out of the architecture. And so that actually kept this trend going since the end of Dennard scaling for about the last 20 years. Energy efficiency has been continuing to improve by several orders of magnitude, even over the last 20 years, even after the end of Dennard scaling. So that's amazing. This is an exponential trend, though. So exponential trends, it's hard to continue forever an exponential trend. And so, and the other thing that's really interesting about this exponential trend is I just heard a talk with Jeff Hinton, after he won the Nobel Prize, and he was mentioning, I came up with a lot of these algorithms for neural networks in the 80s, but people were not impressed because I couldn't get them to work. And so people were very skeptical and thought I was goofy. And he said, well, once in the 2010 range, we had these, basically the computing horsepower to do it. That's what really enabled people to see this power of AI. And so, the person who invented these algorithms and just won the Nobel Prize for it admits hardware was a major, key, important factor in moving all of this forward. And it's going to continue to be. I mean, LLMs are only possible because of this hardware. So the question here is now, things are starting to, possibly stagnate a little bit. And I've been watching this pretty carefully. And, various products that come out, they're actually even more afraid now it seems to show their energy efficiency or energy efficiency in terms of tops per watt. You have to actually really dig to find measurements where you can find that. And so, is this trend going to end? I mean, that's the big question. Or are there new technologies that will drive it forward? And so this is really the key, and that's why I like this chart, spend several minutes on it, because this is really the key that drives me. Is I think this is digital really, the way we're doing things has been running out of steam. And so some of these new paradigms that have been around for a while, but by the time, a prototype is made, the next generation digital has already really, really outshined it. I believe now there may be actually a time coming where some of these emerging architectures really will actually be needed. And so it will be important to push them forward. And this was also, so I worked on this SRC roadmap as well. And actually, I spent a lot of time with Victor Zernoff on some of these charts here. Another way of looking at this is this exponential improvement in energy efficiency has led to an exponential increase in the use of compute energy in the entire world in terms of joules per year. And that's been occurring for the last several decades at least. And you can probably tell that because you see that these companies now are buying nuclear power plants basically to power data centers. I mean, where I am in Arizona, there's data centers going up everywhere, and there's this question of how there's going to be power to supply them. Well, if this trend goes on, eventually you're going to have something where computing is taking a huge amount of the world's energy production, and then there's going to start to be trade-offs. Just like water in the desert, there's this fight between semiconductors and farmers. Well, there's going to be a fight between air conditioning and data centers. And this also highlights the need that the only way for this to be sustainable is to continue our exponential improvement in energy efficiency, because otherwise the total compute capacity of the world basically is going to be limited by the amount of energy that's being willing to be dedicated to computing. Okay, so that's the grand challenge. I mean, and this was actually something that we used for the CHIPS Act and some of these other things in the US. Okay, so where are we now? So I mentioned it seems like things are somewhat stagnating. Well, I've been looking for the last 10 years or so, and we're really around about 1 to 5 tera operations per second per watt. And I've actually looked more recently. I didn't have a nice graphic, so I didn't put it up here, but even the new Blackwell and some of the other new TPUs are basically in this same range. So the TPU V7 and the Blackwell are both still within this 2 tera operations per second per watt range. So at least for the last 5 years or so, for an 8-bit Mac, multiply accumulate, we're not really vastly improving our energy efficiency. Now, it's harder to find these numbers now, but you can find them, and you can find tests people have done. And so that leads then to the question, so basically, the only way, and I heard some discussion, basically OpenAI and all of these companies are wondering, how are we going to even be able to deploy these existing advanced AI features that we already have, much less some of these new ones that we can do on smaller machines. How are we going to deploy and develop new AI capabilities when they're too power intensive almost already to really deploy to the public? And so, essentially they are relying on us as hardware people, as all of us in this, call, I think for the most part, as hardware enthusiasts, to show them where will the next 2 orders of magnitude come from. And I don't even know that, NVIDIA has the answer to this right now. And so I think, this is really the big question, I think. Okay. And so there's, a number of answers. There's things that are further out, like quantum computing. My answer, though, to this is that, I think the time is right for analog in-memory computing to work. And what is analog and memory computing? Well, just a very super brief, simple summary that I like to show my students. So CNNs and even LLMs all have a lot of vector matrix multiplies, basically vector and matrix math at the core of them. Okay, so convolutional and multi-layer perceptrons especially have this vector matrix multiply operation constantly. And what that operation is, simply is if you have this V and this W here, V1, W11, V2, W21, V3, W3, you multiply each of those, and then you add them down this column and you get this sum here. So the interesting thing is there's a very analogous operation that you can do electronically, where you take a voltage and you apply it to a conductance and you get the product Vg just by applying that voltage to that conductance. And if that conductance is tuned to represent the same weight element on the left side, then you'll basically have a current coming from this that's proportional to that product, and these products can be summed, and that's going to be proportional to the sum at the bottom. So basically your output current in this case is summed, and so mathematically that's equivalent to this logical electrically this is equivalent to the logical operation on the left. When you do the logical operation on the left, the challenge is in using kind of a standard digital architecture, you're going to need to move the data from registers, this V and W, the numbers represented to registers, to ALUs, basically to various logic registers. And there's a ton of moving, shuttling data around, and that really eats up a lot of your latency and energy. When you do this on the right, the weights stay still, and you actually get the operation for free in parallel. And even similar digital parallel operations cannot quite, if you do everything right and reduce the energy efficiency of your, reduce the energy or power of your ADC, this can give you orders of magnitude more efficiency than possible with similar digital architectures. So then how do we map this to a convolutional neural network, for example? Well, it's actually pretty complicated, so I'm not going to go into all the details. But you can map basically the arrays that I showed you, these simple kind of arrays of non-volatile memory elements that are programmed to represent the weights in a, say, convolutional layer. You basically will have tiles that have those arrays in it, and roughly each of those tiles can map to one or sometimes a few convolutional neural network layers. The same with the multi-layer. So at the end, you have these multi-layer perceptron. That's very similar. So basically, you have all of these tiles. They have some kind of network on chip, and that allows them to shuttle the results between each other. And so you can basically map a CNN or MLP to a neural network accelerator. So really, the goal here is to create an accelerator like this with all these tiles of these basically memory arrays, and that will be kind of the next generation neural accelerator or neural network accelerator. It's also possible. I mean, people are looking at how to do this for transformers as well and other LLMs, and so that's kind of a future piece of research on the architecture side. It's very well known how to do this for CNNs and MLPs. And you benchmark it using some of these standard data sets, going from things like, you'll see things in the literature from MNIST up to ImageNet. It's best to benchmark it on things like ImageNet or actually YOLO, which I didn't write here, because they give you a better representation of how it will be in production. But a lot of work is still done at the kind of CFAR level. I mean, MNIST is considered a little too simple, depending on the accuracy that you can get. But benchmarking accuracy on these data sets is actually very important, as we'll see. Okay, and then the final really kind of important piece of introductory work. So I spent a lot of time, even though I'm more on the device and circuit side, I spent a lot of time kind of really getting into the architecture, because I wanted to convince myself that there was some merit in this approach, and that we really could, achieve something that would be not possible to achieve otherwise. And we did this exercise a few times. I worked very closely with two different extremely talented postdocs I had at Sandia. And we did this first for RRAM. What I'm showing here is for Sonos. So Sonos, which I'll talk about in a minute, the basically flash type technology. So we designed at the circuit level. So we actually worked with an expert kind of ADC designer and actually put these circuits all the way up to in some cases to layout. In this case, they weren't all to layout, but many of them were. And we basically created a numerical model of this entire analog vector matrix multiply core at the architecture. So this is a custom, basically Python model of the whole thing. And we did this twice. We did this for Sonos. We did this kind of separately for RRAM. And in both cases, we were able to show that you can get a peak system level efficiency in the range of 100, basically 50 tops per watt. But if you're able to improve the data movement, which I think is possible, you could actually, the core itself is something like 180 tera operations per second per watt. So remember, what GPUs are operating at now is about 1 to maybe 5 at the most. And so if we were able to really use this at the peak of 50 to 100 tops per watt, this is going to be a very important tool, I think, to get the whole community to the next order of magnitude. Okay, and I just also wanted to mention very briefly, I'm now leading a large project looking at using this for space, and in space, all of this is extremely important because they no longer can send data down to data centers to process it. You actually have to process on a satellite itself, and so now we're spending a lot of time looking at these things and making sure that they're also radiation hard and able to deal with various temperature swings and things like that. But the idea is exactly the same. In fact, we'll go to the next slide here. The systems that we're looking at that we would implement in space, the greater your energy efficiency in terms of, say, tops per watt, the greater the resolution that you can have in, say, an integrated sensor like a focal plane array. And so this is one of our exemplar applications, is a focal plane array, which is basically an infrared camera that looks at Earth from space and tries to detect various things. Often right now in a satellite is sending all of that data to a GPU to look at it in neural networks. We are looking at integrating analog in-memory computing with resistive memory directly into this readout array. So basically directly into the camera itself. And by doing that, we can make this about 10 to 100x higher resolution because the tops per watt is directly proportional to the resolution we get on this camera. So anyway, this is just another application. It's a little more niche, but it's something that I'm very interested in right now. Okay, so technology side. Now the rest of this talk is going to be about technologies and memory devices. So, and I know it's titled Emerging Memory. But I'm actually going to start off by talking about flash memory because I've been working a lot on Sonos, and I think this is a good baseline to see. And then the rest of the talk will be on resistive memory, which is a emerging memory, but it's fairly common, and probably many of you have heard of it. It's still considered emerging, but there are a number of prototypes. And electrochemical RAM, this is a much newer emerging memory that I was involved with the invention of at Sandia. And we're continuing to mature, and it's starting to make its way into fabs and smaller scales. Okay, we're also looking at. I'm not going to cover conducting bridge RAM today, but yeah, all four of these we're looking at ASU, and in the past I've been involved in these others as well. I don't have ferroelectrics on here because it's not as common, and STT-MRAM because they're not as common that they're analog. But I mean, there are a number of other devices as well that people are looking at. Basically to serve as these synapses. All right. So with all these potential advantages, why are we not using analog today, especially with, for example, with technologies like flash? Well, and the reason is because analog is difficult to achieve the same accuracy as digital, as you might guess. I mean, analog, using these devices in analog sense creates accuracy challenges. And with digital, you never have to really worry about accuracy. As long as the device is working, there's no real accuracy challenge because it's pretty much deterministic. If you have any errors, they'll go through error correction algorithms, but in general, the bit errors are very low on modern digital systems. And so you don't have to worry about errors at all. Analog, you're actually mapping a bunch of neural network weights to individual analog devices. And this is kind of where the big efficiency boost comes from, is being able to do that. But then every device non-ideality that you have is going to give you a little bit of weight error, and that will ultimately affect your neural network accuracy. Okay, so if you look at digital multi-level memory here on the right, actually, you have all of these different states which are neatly separated, and you make sure that you're this is just basically a histogram of devices versus conductance. You make sure that these never cross over. In analog, it's actually fine for all of your weights to kind of cross over and overlap with each other, because at the end of the day, you're actually summing up about 1,000 devices along a column. And so really what matters is the precision of that sum, not the precision of each individual bits. And so we actually have several papers kind of explaining why this is. So you don't have to have in analog the weights be separated like they are. In fact, that's not useful to try to do that. But you do need to have the accuracy of the dot product, okay? And what causes the accuracy of the dot product to be diminished? Well, basically when the mean and sigma of these are these weight devices that are mapped to weights are too far off. And what causes that? Well, several things. So, I mean, first of all, just when you first program it, there's some limit to how precise that you can program it. So you get these spreads, and that's fine. Then you also get drift, and so these spreads will occur. These spreads here that you're seeing will increase over time. So the sigma of each of these will increase over time, and they increase as a function of conductance. And then you also have noise, which isn't really shown on here, but it would contribute to the apparent wideness of these. And then the other thing, I mentioned I'm looking at using these devices in space, so that adds some additional challenges like temperature swings and radiation, and so all of that causes challenge. And the big challenge here also is that we want to really industry benchmarks like MLPerf basically say that we need to have 99% of the digital system accuracy. Okay, so that's really the challenge, is that we need to be pretty close to GPU level accuracy, where GPUs are using these 8-bit weights. That doesn't mean that we need to have 8 bits actually of discrete levels. That just means when you look at the whole system, the accuracy needs to be 99% of the 8-bit floating point digital accuracy, or 8-bit int in some cases. Okay, so what actually causes error that degrades this? And I was mentioning this on the other page. This is just kind of a plot showing schematically what the error sources are. So in terms of the conductance deviating from the ideal, so ideally the conductance would just be fixed at some exact point from the time you program it, basically going on forever. But in reality, you have things like read noise. It turns out in our cases, read noise is not very severe, so it actually wouldn't hamper actually too much. Then you have things like relaxation that may occur after you program on the order of milliseconds to days. And then finally, you have things like retention drift, which occur over years, which occur in normal non-volatile memories. So all of this can be characterized by a conductance error, and we'll talk about this a few times. And then, when you try to use this for a training accelerator, you get into even more complex. I'm not going to go into these in detail just due to time, but when you try to make a training accelerator, not only do you have to have stability be excellent, you also need to have your programming, the device programming behavior needs to be almost perfect. So every time you pulse it, it needs to change the same amount, and that's challenging certainly with some memories. And then finally, what this all led to is really that you have to basically model accuracy with an understanding of the devices and circuits at the kind of algorithm and architecture level. So we at Sandia have developed a tool called when I was at Sandia, I'm still working on this tool at ASU, but called CrossSim, which basically takes a bunch of device characteristics and models accuracy at the algorithm level. So this is something that's new, that's been needed for things like for architectures like analog in-memory compute, because the algorithm level device, the algorithm level accuracy is so dependent directly on devices. So you don't need something like this if you're using GPUs to run your algorithms. But when you're using analog devices, you really need this full cross stack. And so this has really encouraged a lot of collaboration. I think as was mentioned at the beginning of this talk, really the algorithm side has to understand kind of all the way down to the device side and materials effects because they're actually directly affecting the algorithms. Okay. All right. So now on to the three devices that I'm going to talk about. And Sonos, I'm just going to talk about briefly because Sonos is very important. So let me just go to the first slide here. And Sonos, Sonos stands for semiconductor oxide nitride oxide semiconductor. And this is a basically mature commercial technology. Originally, actually, Sandia was one of the pioneers, so I was very familiar with it. And it has replaced floating gate as flash, and that's because basically Samsung VNAND was based on Sonos, actually Tanos, but it's almost the same thing. So it's a type of charge trapping memory, and it's replaced floating gate for the most part when they went to vertical flash, because it involves charge that is localized, and so that was just more convenient when they made vertical flash. So Sonos device basically looks like a MOSFET, except you have a kind of thickened gate stack. This nitride. Basically, you can think of just a nitride inserted into your gate stack of your MOSFET. And if you inject charge in that nitride, you're going to increase the threshold voltage on an N MOSFET here, right? Because it's harder to form the electron channel when you have all these electrons here in the nitride. And so that's called programming. And you can erase it by pulling that charge out. Typically, the charge is injected and removed through tunneling to the channel. And so we've been working a lot with Infineon, which has a 40 nanometer NOR Sonos, embedded Sonos. So Infineon is interested in this analog in-memory compute application and using their embedded Sonos. Whereas the Sonos in your phone is flash and is NAND flash, and so NAND flash is much harder to use for analog and memory compute, although it's ultra dense, and that's why you use that in your phone. And so anyway, we've looked quite a bit at the array ways to implement this in array, and I'm just going to show very briefly some of where we're at with Sonos. So this is what the cell looks like. This is what the Infineon 40 nanometer cell looks like, and they're working on more scaled cells, and they'll be publishing on that soon. But we've been working a lot with this 1024 by 1024 prototype, basically prototype analog in memory compute chip, and the weights are stored basically as a function of the threshold voltage. And the state is related to the drain current in sub-threshold. So when you change the threshold voltage of Sonos, you actually exponentially change the drain current in sub-threshold. And so that's really nice because that gives you a huge dynamic range of about 4 or 5 orders of magnitude dynamic range, which is great. So this is what Sonos, and then you can basically just translate this to a conductance. I know I've been talking mostly about conductance, and there's an equivalent conductance of a Sonos just based on that current and your read voltage. And so this is what it looks like if you're programming, say, 8,000 devices into these conductance bins. You can see the device-device variation. And then ultimately, this device-device variation is characterized by this conductance error. So this is just a real plot of this conductance error, which shows the sigma of each of these devices here. And this is ultimately what will determine accuracy. So if we look here, we spent a lot of time kind of modeling and basically using these Sonos to perform things like ImageNet simulation and actual ImageNet inference. So when we look at kind of where Sonos is at, and we're working on improving this as well, but if you look at floating point, so 76.46 would be the accuracy target that we're trying to hit. Now, with an ADC, we're already going to lose about maybe 0.4% in accuracy. And then when you actually implement this on Sonos, you lose another approximately a little less than 2%. Okay. So immediately after you program Sonos, it's pretty close to meeting that ML-perf target on ImageNet. Not quite there. And this is really the kind of the remaining challenge with Sonos is that it needs to get to the full, kind of within the 75 to 76% accuracy range. And then the other challenge is that it will lose accuracy over time. And so then you have to basically, you'd have to correct this by refreshing. And so in this case, you'd have to refresh it probably every few days to maintain its accuracy. So this is just showing that, it's kind of showing that drift. So as it drifts, you're changing your mean current or your mean basically conductance, and you're changing the variability. So the drift does not occur at the same rate in all of the Sonos devices. And so you can see basically this spread widens, distribution widens, and the mean changes. Typically in this case, it's reduced. And so this is what's on that last slide. This is what's causing that accuracy degradation in Sonos. Okay. The other thing, so that's kind of where Sonos is at, and that's really one of the remaining research challenges and that we're looking at with Sonos is how do we actually fix this accuracy gap, and that can potentially be done by noise-aware algorithms, and that's kind of one of the things that people are looking at. Okay, and then the last thing I'm going to mention on Sonos, which is kind of interesting. So Sonos. We since it's a commercially mature technology, we were looking at using this in space. And Sonos has a little bit of a challenge in space because of the charge-based memory. And so when you're in space, when you're subject to ionizing radiation, you end up actually removing some of this charge from the nitride. And that causes, when you remove charge, you reduce the threshold voltage. And so that changes the state basically of these devices, causing it to incorrectly represent the weight. And so what we have seen here is as you subject this to radiation, your Sonos basically current distributions, which are directly mapped to your weight distributions, broaden and kind of move toward the wrong weight values. And so this degrades your accuracy. And so this is a challenge. Basically, your accuracy versus your dose in space is degraded. And so after, say, 10 kilorads or so, you would start to lose accuracy. And that represents actually possibly about a year in space. So it's not terrible. But right now, we're working on 2 algorithm level corrections that we believe will extend this to 40 to possibly 100 kilorads. And that would be enough for almost any satellite level mission. So anyway, Sonos, we think, has a lot of promise, and could be one of the first analog in-memory compute devices that we see. But yeah, the remaining challenges are these, drift, radiation tolerance, as well as scaling. I mean, Sonos is a charge device, as you may remember with Flash, when they were trying to scale planar Flash, we won't be able to scale forever. There will be some scaling challenges because you get to a point where you only have a few electrons left in your nitride. Okay, so that's Sonos. So let's go to RRAM. RRAM, as probably many of you are familiar with, so this is a technology that I've worked on for I guess more than a decade now, and this is what the tantalum oxide device looks like. Another name for this is memristor. So HP popularized that name. I don't know, about 15 years ago when they basically equated this to this missing circuit element. But what this actually is, so this is a non-volatile memory where the current really flows through this filament, is what this middle part here is showing. So this is a filament in a metal oxide. So in this case, my device usually uses tantalum oxide. And all of the current for this device flows through this constriction here. And you can program the resistance of this device by applying a field and a current. And the field and current, basically, the current adds heat, allowing you to generate vacancies. So what these little guys are here, by the way, are vacancies. And so vacancies act as N-type, basically N-type dopants in tantalum oxide. So when you have oxygen vacancies, it allows more current to flow than when you just have fewer oxygen vacancies. So when you apply a voltage, you have a current flowing, you're able to basically pull oxygen out, create more oxygen vacancies. And you're able part of the reason you're able to generate those vacancies is because the current's flowing through it, heating it up. You wouldn't be able to do that at room. It's very hard to move oxygen or vacancy. You're always kind of moving the oxygen, but vacancies are a way to think about it. But you can't really do that at room temperature. It's the activation energy is too high. And so having this current flow through it allows this device to work. Okay, so anyway, you can by applying opposite polarity voltages, you can increase and decrease the conductance of a tantalum oxide or any of these metal oxide RRAMs. So I have developed an entire process both at Sandia and I've redeveloped at ASU that I can basically integrate. So I get a wafer back from a foundry and I can integrate this RRAM onto that wafer and I can make large arrays of that. And so right now we're in the process of doing this for a 128 by 128 array. And then hopefully next year we're going to do that for a 256 by 256 array. So we're getting wafers right now, 200 millimeter wafers from commercial foundry, and we're integrating onto these arrays. And so we're going to hopefully demonstrate in the next year or so a 128 by 128 analog in-memory compute chip based on this process applied to commercial CMOS. And this is one of the chips. So right now we have a 32 by 32 chip that we've done this with, and this is the array characterization platform that we developed. It's actually kind of a special platform in that we have the RRAM in this case is in an interposer, and the CMOS circuitry is on the right side here, bump bonded to the interposer. We did this in part for radiation testing reasons, basically so we could protect the circuitry and test only the radiation on the RRAM here. But anyway, this is kind of our first variant. We have a few other variants, many of them where just the RRAM goes directly on top of the circuitry. Okay, so go here, slide. Okay, so RRAM. So I mentioned so we can just like Sonos, we can program all of the RRAM weights to all of the RRAM conductances to represent neural network weights, just like we did with Sonos. But there's some challenges, and the biggest challenge that we're experiencing right now with RRAM is after we program it, a few of the RRAM devices, this does not happen, say with every device. In fact, it's only a small percent, maybe less than 10%. After you program it, they tend to have this pretty sharp drift. And sometimes it occurs within less than a second, but they will depart from their conductance by maybe say 1 to 10%. And sometimes it happens within a second, but sometimes it actually happens later, and there'll be drift over the course of an hour. So this has created a problem, which I'm going to show on the next slide. The other problem, which you hear a lot about, is random telegraph noise. And this is kind of a plot showing what kind of typical random telegraph noise looks like. And it's actually less of a problem, at least in our devices, as far as the accuracy. The biggest problem for inference accuracy with tantalum oxide RRAM is this one on the left. Which is this stability after programming. Okay, and we spent a lot of time recently kind of coming up with statistical ways of characterizing this. So we have a paper that's about to come out in TED in the next. I mean, it was accepted, so it should be out in the next week or two. So this is some of the work from it. But basically, the standard deviation of a set of devices in an array versus time is kind of the best way to characterize accuracy. So really this, in particular, the device-to-device variation, sigma g, and I won't go into all of them just due to time, but that's really the thing that that's the one kind of statistical parameter that is really heavily causing accuracy problems for our RRAM. And this is true in the literature as well. I mean, there's been a number of papers, including in Nature and some other kind of high impact journals discussing this problem. Although there was one from Stanford and UCSB showing that they could fix it through device aware training, which is true. You can do that, and we're looking at that as well. But we want to get the devices as error free as possible before applying algorithm level fixes, because the higher level fixes always have some energy efficiency cost. And so then if you end up being not energy efficient, not more energy efficient than a digital system, then there's no point in having an analog system. So Anyway, this purplish curve here, though, this is the real challenge. And basically, if you look at, when we first program the devices, this is just a probability density curve here of the actually KDE here over the top of our devices when we first program it. They're fairly tight, and the sigma g is reasonably low, but still some not perfect. And it gets much worse though over time as some of these spread out. And a lot of this is just due to a handful of these kind of troublemaker devices which have this longer term drift. And so we spent a lot of time trying to understand over the last year what's causing that. Is it cycle to cycle, or is it device to device? If it's cycle to cycle, that means it's probably something more inherent. Device to device might mean it's how we're making the devices is a problem. And what we concluded is it's both. I mean, a lot of people have said, there's been a lot of papers saying cycle to cycle is dominant in RAM because of the filament. Um, we've actually seen that it's both. So basically, the cycle to cycle variation can range from much less to much higher than the device-to-device variation. So some devices are prone to more bad cycles than other devices. And so what that means, though, is even the bad devices can have good cycles. So even the ones that are prone to bad cycles sometimes have good cycles. And so that's kind of what this is all just showing statistically. And I'm just showing you here, but the paper will be out in a week or two, so you can take a look if you're interested in the details. But this sort of led us to kind of physical understanding, which is also corroborated by some other work. This is by Rainer Wasser's group, published several years ago on strontium titanate. But basically, the behavior that we're seeing, which is kind of conductance drift that occurs at different rates. Can be attributed to these different conductive pathways that are kind of competing, and you can have many different conductive pathways that result in the same conductance. And so you can achieve the same conductance by different ways, but if you achieve it the wrong way or in a non-optimal way, you're going to have a lot more drift than if you achieve it in the right way. And so based on this, we came up with a programming routine that we added, basically a modified write verify routine that checks our filament stability after setting it, and it actually only checks it for about 1/8 of a second. But if it detects that that's a non-optimal filament configuration, it just completely reprograms that device. Again, it just moves it and then goes back to the original filament configuration. And that gives a huge improvement, especially across some conductances in that error, in particular this error on the bottom, which is this sigma g. And so ultimately, if you look here on the right, this is kind of the most important thing, is that we can improve the accuracy, the inference accuracy by a huge amount by using this technique. Now it's still not perfect, and this is just CFAR 10, but it's gotten much better. And so then we're going to apply some of the noise aware training. But an interesting thing to note here is that if you only look at read noise, the level of read noise that we're seeing wouldn't affect the accuracy at all. So read noise, this green curve here just shows you that read noise is not actually a problem at all. It's really this conductance drift that occurs after you program it. And I think there's going to be, based on what I see, there's going to be a lot of work coming out trying to address this. Oops. Okay. And then one other thing I'll note on RM is the conductance depends on temperature, and the temperature coefficient of conductance actually depends quite a bit on the conductance range. And so this is some temperature measurements that we've made for the different conductance states. And depending on if you're in this sort of high conductance state, you have a metallic transport with a lot of scattering. And so you have this negative, basically, coefficient of conductance. And you have sort of the opposite. You have a semiconducting behavior, low conductance. Well, this creates kind of an accuracy challenge as well, that when you have temperature swings. And we have a paper that we're preparing. So there's basically kind of simple column level methods, and I'm not showing all the detail here because it's undergoing preparation right now, but there's column level methods that we think at the kind of, I would say, almost circuit or lower algorithm level that will actually be able to correct this, we believe. with a relatively low overhead. But this temperature variation alone, and this is similar for phase change, by the way, TSMC had a paper on this in phase change. This is another issue that's a big challenge for analog and memory compute is temperature. And this has not been very well addressed. So I think in the next year, you're going to see a lot of work on this because even if we get the baseline accuracy down, I mean up, the baseline accuracy up for say ReRAM and even for Sonos, being able to operate in a normal temperature range is a challenge that has not yet been fully addressed. And so, as you know, a GPU can certainly operate in a full kind of, 0 to 85 C temperature range. So analog has to be able to do the same thing. And this is more of a challenge for analog. Okay, and then finally, RRAM, the good thing about RRAM, one of the reasons we're really looking at it a lot is very immune to radiation. There are some subtle kind of interesting effects that occur that I'm going to be putting together and showing in the future. But in general, the large scale behavior, you can go up to a very 8 megarad would be like a deep space mission. You could go all the way almost to Jupiter with 8 megarad, and you don't see huge changes. So anyway, this is a good feature of RRAM. Okay, now finally, I'm just going to talk about ECRAM, and this is probably some of the work that I'm the most excited about. This is an emerging device that is basically was originally developed to solve some of the problems for training. So we actually developed in this project that I was leading the hardware effort for. We realized that RRAM has a very stochastic programming behavior. So if you want to have a training accelerator, everything I've been talking about for the most part so far is inference. But if you want to have a training accelerator, when you program a device, when you pulse it, the conductance needs to change almost with a perfect predictability, and it needs to be the same no matter what conductance it's at. And that's just not true of RRAM. And so these issues like nonlinearity and asymmetry and then cycle-to-cycle variation and device-to-device became a big deal. And you still see these in a lot of papers. And I do want to emphasize, this is all related to train. These are all training properties. Now, training accelerators, I think, are much further out. These are more than 5 years out, I think. That's why you can see, IBM, for example, shifted from doing a lot of work on training to mostly inference right now, because inference is really the near term goal. But so training, so the nonlinearity and asymmetry, these kinds of things are for training. These are a huge challenge for RRAM, which I'm not sure how you'd overcome with filamentary conduction. And that's really where ECRAM came from. And this is the original device that we invented at Sandia, because my colleague Alec Talon was working on a battery, and he said, well, a battery has very linear programming behavior. So if you charge a battery, you change the conductance in its cathode very linearly with the amount of basically the pulse length. And so the first device was just a modified lithium-ion battery. Then we had a collaboration with Stanford where we created a proton version of the device. And this also showed excellent training characteristics, and it was much faster. And then the problem with lithium also is it's not CMOS compatible. So this solves some of that problem. So protons now are kind of one of the main ions that IBM and MIT are looking at for training accelerators. They don't have protons have a very low activation energy, so they're actually not good for an inference accelerator, but they're excellent for a training accelerator. And so IBM and MIT have had a number of publications, including in Science, on this over the past several years on protons in tungsten oxide ECRAM. Okay, and the idea here, by the way, is that I'll show it. I'll show it on this one here. So then the most recently invented ECRAM is based on shuttling oxygen vacancies, okay, in and out of a channel. So how all ECRAM works is basically you have a channel, and that's your resistor. And by pulling oxygen out of the channel or putting it back in the channel, you, in this case, change the number of, basically you can think of this as electron donors, so donor defects, and you increase the conductance, the more oxygen vacancies there are. So very similar to RRAM, except that it's a bulk effect. And so and so it requires also heating, just like RAM. So the challenge actually with oxygen EC-RAM is that you have to heat it up to pull oxygen out and create vacancies or to push it back in. But in general, after you cool it down, it's extremely stable. And so oxygen EC-RAM has been another very interesting advancement over the last several years. The most recent work, though, that I want to show here, and run a little bit out of time, but this is kind of the last major thing I want to show, is EC-RAM based on copper. Okay, so the most common EC-RAM right now, I would say, would be proton-based or oxygen-based, and this is they have a huge range in terms of how well their ions move in the channel and in the electrolyte. And I said, well, what about copper? Because copper has been used for EC-RAM, for CB-RAM, for another type of memory for a number of years. It's got an activation energy right between those two, so it should be good enough for retention, but you could program it without having to do this huge amount of heating. And it turns out that yes, you can use it for that. And actually, copper is very synergistic with using it with protons. So what we found out is that you can actually have a device where you have both copper ions modulating the conductivity of the channel and inject protons. So you can have this stable long-term retention from copper, and you can have a shorter term on top of that conductance modulation based on protons. And so we call this a dual ion EC-RAM. This is something that we just published and are pretty excited about. We spent a lot of time kind of trying to understand the physics of the interaction of these two copper versus protons and controlling them separately. But one thing we did find with the copper state is that it has extremely accurate, extremely good properties for inference. So it has extremely finely tunable conductance levels. The noise is extremely low. And so if you look at some of these, and then the retention also here is extremely high. So ultimately, when you put all of this together, the characteristics that I was looking at before, the read noise and the conductance variability are orders of magnitude lower than they would be for RAM or even for Sonos. And in fact, this copper state on EC-RAM is able to maintain almost perfect inference accuracy for a week. So none of the other devices are able to have perfect inference accuracy at the device level. And then it maintains reasonable accuracy even for about a month. Okay, and this is, you can see here, compared to Sonos. So we're really excited about this. This is, of course, a very low TRL right now. It's not mature, but we believe this may be a promising device that allows you to have both inference and possibly training together. And since I'm running out of time, I don't want to keep you guys. I'll just show. I mean, the dynamic properties are allowing us to look at things like reservoir computing, and so we're working quite a bit on that now, and we'll be showing more on that in the future. And then finally, there's a lot of work I just want to acknowledge on using these devices for extreme environments. So there's actually been EC-RAM that has retention at as high as 600 C. So this could allow you for some sort of extreme environment applications. There's no memories that can do this right now. So my buddy Yi-Yang Lee, who's at University of Michigan, has been developing this. And so we could have, inference in possibly these sensors, say, in like oil wells and things like that. And then finally, also, we've done a very extensive look at radiation behavior of EC-RAM. And there's some very interesting behavior that occurs. It's more sensitive than RAM, but it looks like it still would be okay for space. So if you're interested, I encourage you to look at some of the publications that we had in the last few years showing kind of the detailed physics, both of TID and displacement damage in tungsten oxide-based EC-RAM. Okay, and so with that, I just want to kind of summarize. In fact, let me just summarize on this page because I think this is the best summary, and then I'll end and I can stay around for questions. So if you look at kind of the device landscape right now, the devices that are being really seriously considered for analog and memory compute would be RAM, phase change, Sonos, EC-RAM. And these devices are kind of most important because they have analog behavior. If you look at ReRAM and Sonos, they're pretty good for inference, but they still need definitely some improvement in the stability and RRAM, for example, and phase change both. I think you're going to see a lot of work on that over the next year. Uh, ECRAM, I think, has the ability for training and inference, but it is much newer and there's a lot of progress being made, but it's not yet, fully integrated in CMOS. Although IBM has some early demonstrations of ECRAM in CMOS. So I think, this has a lot of potential, and this is an interesting kind of emerging research area that we're going to see more papers on this. Okay, so with that, I will just leave the summary up, but I want to make sure there's a time for anyone to ask questions if you want, and I can stay for uh, several minutes if anyone wants to ask questions. So
Thank you very much, Matthew. Let me stop the recording.
Subscribe the channel to get the instant updates on our webinars.